The year is 2125. A century has passed since the transistor first revolutionized our world. In 2025, transistors, those tiny switches etched onto silicon chips, were the engines of the information age. They powered our computers, our phones, and our lives. Today, the silicon transistor seems almost archaic, a relic of a bygone era. We have entered the age of the quantum transistor, a device of unimaginable power and potential. Imagine a world where computers are not limited by the laws of classical physics. Imagine a world where transistors are no longer made of silicon, but of exotic materials like graphene and topological insulators. This is the world of 2125. A world built on the foundations laid by the humble transistor. The journey from the silicon transistor of 2025 to the quantum transistor of 2125 is a testament to human ingenuity. It is a story of relentless innovation, of pushing the boundaries of science and technology. And it is a story that has only just begun. In 2025, the world ran on silicon. This abundant element, found in common sand, formed the heart of the transistor. Transistors are essentially microscopic gates that control the flow of electricity. They can switch on and off billions of times per second, forming the ones and zeros of the digital world. There were two main types of transistors in 2025. The bipolar junction transistor, or BJT, and the metal oxide semiconductor field effect transistor, or MOSFET. Both relied on the semiconducting properties of silicon. This meant that silicon could be manipulated to conduct electricity under specific conditions, making it ideal for creating the on-off states of a transistor. These silicon transistors were marvels of miniaturization. Millions, even billions, could be etched onto a single chip, each no larger than a virus. This allowed for incredibly powerful computers and smartphones that fit in our pockets. Yet, even as silicon technology reached its limits, researchers were already looking beyond to the materials and technologies that would define the next century of computing. The limitations of silicon were becoming increasingly apparent by the mid-21st century. Heat dissipation, miniaturization limits, and the speed at which electrons could move through silicon were all bottlenecks. The search was on for new materials and transistor designs. Graphene, a single layer of carbon atoms arranged in a honeycomb lattice, emerged as a leading contender. It was incredibly strong, conducted electricity better than any known material, and could be switched on and off much faster than silicon. Topological insulators, materials that conduct electricity only on their surface, offered another path. Perhaps the most revolutionary development was the quantum transistor. Unlike conventional transistors, which rely on the flow of electrons, quantum transistors exploit the strange laws of quantum mechanics. Specifically, they use the spin of an electron, a quantum property that can be up or down, to represent ones and zeros. This allows for significantly faster processing speeds and opens the door to entirely new forms of computing. While transistors are the foundation of digital circuits, their ability to amplify signals is equally important. The BJT, with its 3 layers of semiconductor material, excelled in this role. In 2025, BJTs were commonly found in audio amplifiers, boosting weak electrical signals from microphones and music players into a form that could drive speakers. The BJT achieved amplification by controlling the flow of a larger current with a smaller current. This small current applied to the base of the transistor acted like a valve, regulating a much larger current flowing between the collector and emitter. This allowed for the amplification of weak signals, making them strong enough to power speakers and other devices. Beyond audio, BJT amplifiers found applications in radio receivers, television sets, and even medical equipment like hearing aids. They were essential components in a world increasingly reliant on electronic communication and entertainment. Section 5. The MOSFET Revolution, from Computers to Starships. While BJTs dominated the world of amplification, MOSFETs were the workhorses of digital circuits. Their ability to switch on and off with very little power consumption made them ideal for building the complex logic gates of computers. In the latter half of the 21st century, MOSFET technology advanced in leaps and bounds. Miniaturization continued, with transistors shrinking to the atomic scale. New materials, such as hafnium oxide, replaced silicon dioxide as the gate insulator, further improving performance. By 2125, MOSFETs were no longer confined to silicon chips. They were used in flexible displays, wearable electronics, and even implanted medical devices. Perhaps the most ambitious application of MOSFET technology was in spacecraft propulsion. By the 22nd century, scientists had developed ion thrusters that used arrays of microscopic MOSFETs to accelerate ions, providing a highly efficient form of propulsion for interstellar travel. Section 6. The language of amplification from electrons to qubits. The principles of amplification remained constant even as transistor technology evolved. Whether it was a BJT amplifying an audio signal or a quantum transistor manipulating qubits, the goal was to control a larger output with a smaller input. However, the nature of this control mechanism changed dramatically with the advent of quantum transistors. Instead of relying on the flow of electrons, quantum transistors manipulated the quantum states of particles like electrons or photons. These quantum states, known as qubits, could exist in a superposition, simultaneously representing both 0 and 1. This allowed for a fundamentally different type of amplification, one based on the principles of quantum mechanics. Quantum amplifiers could amplify signals with incredible precision and sensitivity, far beyond the capabilities of their classical counterparts. This had profound implications for fields like quantum computing, quantum communication, and even our understanding of the universe. Section 7. A concert hall in your pocket then and now. In 2025, a high-end audio amplifier was a thing of beauty. Audiophiles would spend thousands of dollars on amplifiers that used carefully selected components and sophisticated circuitry to reproduce music with stunning clarity and fidelity. These amplifiers, often built around powerful BJT transistors, were bulky and power-hungry, but delivered an unparalleled listening experience. Fast forward to 2125, and the audio landscape has been transformed. Quantum audio amplifiers, no larger than a grain of rice, deliver sound quality that would have been unimaginable a century ago. These amplifiers use quantum interference effects to eliminate noise and distortion, reproducing music with perfect accuracy. The concert hall experience is no longer confined to a physical space. With quantum audio amplifiers and advanced noise-cancelling technology, you can have a symphony orchestra playing in your ears, indistinguishable from the real thing. Section 8. A century of innovation, the transistor's legacy. The journey from the silicon transistor of 2025 to the quantum transistor of 2125 is a testament to the relentless pace of technological innovation. In a century, we have moved from transistors etched onto silicon wafers to devices that manipulate the very fabric of reality. This evolution has been driven by our insatiable appetite for faster, smaller, and more powerful technology. It has also been fueled by our fundamental desire to understand the universe and our place within it. The transistor, in its many forms, has become an indispensable tool in this quest. The transistor's legacy is not just one of technological advancement, but also one of societal transformation. It has connected us in ways that were once unimaginable, democratized access to information, and empowered us to solve some of the world's most pressing problems. Section 9. Beyond 2125. The quantum frontier and the importance of the past. As we stand on the cusp of the quantum era, the future of the transistor seems limitless. Quantum computers, powered by millions of interconnected qubits, promise to revolutionize fields like medicine, materials science, and artificial intelligence. Quantum communication networks, impenetrable to hacking, could usher in a new era of secure communication. Yet even as we explore these uncharted territories, it is crucial to remember the lessons of the past. The fundamental principles of transistor technology, developed over a century ago, remain relevant even in the age of quantum computing. By understanding the history of the transistor, we gain a deeper appreciation for the power of human ingenuity. We also gain the knowledge and inspiration to continue pushing the boundaries of what is possible, ensuring that the transistor's legacy of innovation continues for centuries to come.